Question 1, we want to make a confidence interval for the population mean. Our population is homeowners in a certain area, so we want to make a confidence interval to estimate the average amount that people in this area pay on their mortgage. To estimate the population mean, to create this confidence interval, we've collected a sample mean. So our sample of 120 homeowners, our sample mean from that sample is $1,575 a month. And we know the population standard deviation is $215. So first let's figure out what we know already. So our parameter that we want to estimate, the thing we're trying to estimate that we don't know, is the population mean, which we usually denote with the Greek letter mu. Our estimator, the thing that we're going to use to estimate the population mean, is our sample mean. And our point estimate, the value of our estimator that we have, our sample mean, is 1575. So let's figure out what's the distribution, the sampling distribution of our sample mean here. So we know that we have a random sample because it told us that. And it told us that our sample size was 120. And we know the population standard deviation is 215. So the population standard deviation is known, and it's $215. So by the central limit theorem, I'll abbreviate it here with CLT, we know that our sample mean is distributed approximately normally, with mean equal to the population mean, and standard deviation equal to the standard deviation of the population, divided by the square root of our sample size. Note that we don't know the population mean, remember we're trying to estimate that, but we can calculate this value because we know both sigma and n. We know that the population standard deviation is 215 divided by the square root of our sample size, which is 120. So that's the value of our sample standard deviation. So now we can start making our confidence interval. I'm going to do parts E and F together. So first, what is a confidence interval? All it is it takes our sample mean, and this is our point estimate. What we do is, to make the interval, 95% confidence interval, is we add or subtract a margin of error to it. So we say that our confidence interval is 1575 plus or minus a certain amount, and that certain amount is our margin of error. How do we calculate our margin of error? What is it exactly? Our margin of error which we often will abbreviate with ME, this is equal to a z statistic times our sample standard deviation, the standard deviation of our estimator, which is sigma over root n. Question is, how do we find this z value? What is this z value? And we get this z value from the confidence level. We want to be 95% confident, so we'll find a value alpha, which is 1 minus our confidence level, which is 95%. This is 0.05. So we take 1 minus our confidence level. And what does this value mean? All it says is that this amount, 0.05, is the area in both the tails together. So if this is our z statistic, so our positive z value and the negative version of it. So the total area in both of the tails is 0.05. Remember that the normal distribution is symmetric. So that tells us that the area in each tail, if the total area in the tails is 0.05, the area in each tail is half of that. So that's half of 5%, which is 2.5%. So to find this z value, our z statistic here, all we need to do is find the z-score corresponding to an area to the right of 0.025 or an area to the left of the area to the left of 0.025. If we look up an area to the left of 0.025, that'll give us the negative version. If we look up an area to the right of 0.025, that'll give us the positive version of our z-score. I'm going to look up the area to the left to find negative z. So let me go to my table. I want to find 0.025. I want to find the z-score corresponding to an area to the left of 0.025. So I go in my z-table and I look among the areas, and I find it right here. The z-score corresponding to an area to the left of 0.025 is negative 1.96. So I know that my negative z-scores here is negative 1.96. So this one here must be positive 1.96. So I know my z statistic here. So now I can calculate my margin of error. My margin of error is equal to, I'll move this up here, 1.96 times my sample standard deviation. So that's times, let's see, what was our population standard deviation? Was 215 over the square root of our sample size, which is 120. If I plug into my calculator 1.96 times 215 over the square root of 120, you should get approximately 38.468. And that's my margin of error. That's the amount that I'm going to plus or minus our sample mean by. So my 95% confidence interval is my point estimate, which was $1,575. I'm going to plus or minus our margin of error, which was 38.468. If I plug that into my calculator, I'll first do 1575 minus 38.468. That'll give me the lower bound of my confidence interval. I should get 1536.532. And if I take 1575 plus 38.468, that'll give me the upper bound of my confidence interval. That's 1613.468. This is my confidence interval. What does this interval mean? How do I interpret it? I'm 95% confident that the population mean, which is what I'm trying to estimate, that the population mean is between $1,536.53 and $1,613.47. That's my 95% confidence interval. So just as a recap of what we did, we had our point estimate here, our sample mean. That was 1575. So to make our confidence interval, all we have to do is find our margin of error. And then we just take our sample mean plus or minus our margin of error. And that gives us our interval. How did we find the margin of error? The margin of error is we find a z-score corresponding to 95% confidence. That's what we did here. And we multiply our z-score by the standard deviation of our estimator, the standard deviation of the sample mean. Remember, we get that from the central limit theorem. So I just plug in the numbers that I have, sigma and root n, and I get my sample standard deviation. I multiply those two things together, my z-score and my standard deviation, to get my margin of error, which is about $39. Next, the question is the true population mean included in this interval? Well, do we know what the true population mean is? We don't. That's what we're trying to estimate. So we don't know what the population mean is, so we don't know if it's included in this interval. We're just 95% confident that it is. So to this we say, we don't know for sure that it's in this interval because we don't know what the population mean is. We're just estimating it to be within this interval. Is the sample mean included in this interval? Well, how did we make our interval? We took the sample mean and we added or subtracted a certain amount from it. That's what we did right here. So, since it's at the center of our interval, it's always in there. So yes, the sample mean is at the center. It'll always be at the center of our confidence interval. Why? Because, well, the way we make it is we take our sample mean and we add $39 to it and subtract $39 to it. So we're adding or subtracting the same amount on each side. So it's always going to be smack dab in the middle. Is this statement true? We are 95% confident that the true proportion is included in this interval above. Answer. This is an okay statement. There's nothing wrong with this statement. The only thing that we want you to remember here is that saying 95% confident is not the same thing as saying there's a 95% probability that the true proportion is in this interval. This should actually be true mean. The true population mean. So let me put that in writing. So what's not true to say there is a 95% probability. What's the difference? Why is it not true to say there's a 95% probability that the true mean is in this interval? Well, If you think about it, the true population mean either is or is not in the confidence interval. There is no middle ground. It either is or it isn't between these two numbers. So there's either a 0 or a 100% probability that it's in there. It either is not or it is. So that's why we can't say that there's a 95% probability. We can say we're 95% confident. It's a subtle, but it's an important distinction. All right, in part J, we want to find a 97% confidence interval for the population mean. So the difference between part E and part J is that in part E, we wanted to find a 95% confidence interval. In part J, we want to find a 97% confidence interval. So let's go ahead and do that. So first, remember that the confidence interval, I'll call it CI, is given by our sample mean plus or minus our margin of error. So we know our sample mean. That still hasn't changed. Our sample mean is still 1575. So that's still going to stay the same. We'll have to take a look at our margin of error. So our margin of error, well, and I just write an E, this is equal to a z-score times our sample standard deviation, which is sigma over root n. Sigma, our population standard deviation, is still the same. It's still $215 as we were told originally. Our sample size is still the same. It's still 120. Let's think about the z-score. How did we find the z-score in part E when we had a 95% confidence interval? Well, to find the z-score, we figured out that because we had a 95% confidence interval, that means that there's 1 minus 95%, or 0.05, 5% in each tail. Sorry, 5% total in both of the tails. So in each tail, there was half of that amount, 2.5%. So now in part J, we don't have a 95% confidence level, we have a 97% confidence interval. So that means that the total area in both tails is, let's write that down, total area in both tails is 1 minus 97%, so that's 0.03 or 3%. So that means in each tail, we have half of that. Because our normal distribution is always symmetric, half of 3% is 1.5%. So I want to find the z-score with an area to the right of 0.015 of 1.5%, or the z-score with an area to the left of 1.5%. Looking up areas to the left is the easier part, so I'll just go to my table and look up this z-score. Area to the left of 0.015. Let's see. 0.015 is right here. So the z-score corresponding to an area to the left of 0.015 is negative 2.17. So this z-score here is negative 2.17. So this positive z-score must be positive 2.17. So I'll take z equals 2.17, and then I'll plug that in here to find my margin of error. So I take 2.17 times sigma over root n. So that's 215 divided by square root of 120. Remember, we were given each of these two numbers in the original problem statement. So I'll plug this into my calculator. 2.17 times 215 over the square root of 120. This should give you 42.59. So then lastly, I can construct my confidence interval. I'll do this over here. I take my sample mean plus or minus my margin of error, and I get, let's see, sample mean was 1575 plus or minus 42.59. Let me plug this into my calculator, and I get 1532 and 41 cents and 1617 and 54 cents. So that tells me I'm 97% confident that the mean amount, that the average mortgage of all homeowners in this area is between $1,532 and $1,617. Part K, let's suppose that the confidence interval that we constructed in the first part, well, I guess really in part E, is too wide. So we made a confidence interval and it was too wide. How can we reduce the width of our confidence interval? Notice when we talk about the width of an interval, we're basically talking about the difference between these two numbers. If the difference between these two numbers is larger, if these two numbers are farther apart, then we say we have a wide confidence interval. If these two numbers are closer, then we have a narrower or skinnier confidence interval. So the first thing to notice is when we changed our confidence level from 95% to 97%, what happened to the width of our confidence interval? So when we had a 95% confidence interval, our interval was from 1536 to 1613. When we have a 97% confidence interval, it went from 1532 to 1617. So which of these two intervals is wider? The answer is this one right here, the 97% confidence interval. So what we notice is increasing our confidence level from 95% to 97% made our confidence interval wider. And that's a general rule. The more confident we are, the wider our confidence interval is. Let's think about an intuitive reason for that. So to be really confident that my interval contains the true population mean, to be as confident as possible, I want my interval to be wide, right? I want my interval to have the highest chance of containing my population mean. So to be super confident, I should make my interval wide to make sure that it really does contain the true value. So we know that increasing the confidence interval makes our confidence interval wider. This question asks, how can we reduce the width of our interval? Well, to do that, let's do the opposite. So to decrease the width of the confidence interval, we should reduce our confidence level. So instead of perhaps a 95% confidence interval, we should make a 90% confidence level interval or an 80% confidence interval. So that's one way we can make our interval less wide. There's actually another way we can do it too. If you notice, the way that we make our confidence interval is we take our sample mean and we add and subtract the margin of error. If our margin of error is smaller, right? Our margin of error here is 38, here it was 42. Here our confidence interval was narrower. Here, where the margin of error was higher, our confidence interval was wider. So smaller margin of error means we have a narrower confidence interval. So we talked about reducing our confidence level. That affects our z-score. Let's think about the other part of the margin of error. The other part of the margin of error is our standard deviation. The population standard deviation we can't change. That's just a function of who our population is. But if you notice, the sample standard deviation is our population standard deviation divided by the square root of our sample size. If our sample size is large, if n is large, this value becomes smaller. For example, if I divide 215 by 10 versus if I divide 215 by 100, this value is a lot smaller. So if I divide by a larger number, overall the value of this fraction is smaller. So if my sample size is large, the sample standard deviation is small. Sigma over root n, our sample standard deviation is small. So another way to decrease the width of our confidence interval is to just take a larger sample. In other words, make n larger. Lastly, what do we mean when we say 95% confident? This is a little technical. We say we're at 95% confident, blah, 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 that the true population mean is within our interval. That means that in the long run, if I take all the possible samples from my population, of whatever our sample size is. So if we take all the possible samples from my population of size, say 100 for example, if that's what n is, and for each of these possible samples, compute the confidence interval. So if I compute all the possible confidence intervals, then being 95% confident means that 95% of all the possible confidence intervals possible here. Will contain our population mean, our true population mean, mu. So being 95% confident that our confidence interval contains the population mean means that if I took all the possible samples of my desired size and computed all the possible confidence intervals, then 95% of all of them would contain mu.